All right, so I'm going to title this screencast Physics Tools Representing what physicists call constant velocity motion. Constant velocity motion. Okay? And a fancy word for like the physics tools we use to represent constant velocity motion, one fancy word for that is just, these are called scientific, in general, these physics tools are all scientific models. So these physics tools scientists use in general are called scientific models. Okay? So these are some scientific models physicists use to represent constant velocity motion. Okay? Let's see here. First one, I'm just going to say the words, okay, to describe the motion. And let's say we have a toy car, okay, just like you did in the lab. So toy car moves with constant velocity. Okay? And those are the words. That's a scientific model, these words. And we might draw a diagram. Here's another model. A model just represents something in real life. Scientific models, in this case, it's a descriptive model because we're just trying to describe motion. And you may have a diagram that looks something like this. You'll write position. And we measured in centimeters. And we had a little car. You have to be a really good artist, by the way. All my objects look like boxes. Haha. And our diagram might have, we might put positions on here. I don't know how fast this car went. I'm just going to make marks. And then maybe I'll turn my diagram into a motion map. Okay? So I'll write my motion map below it. Now, motion maps are actually pretty useful. A motion map is essentially it shows how velocity vectors change as time moves forward. So it shows how velocity vectors, remember that vectors show two things. They show a direction and a magnitude, okay? So motion maps show how velocity vectors change as time moves forward, or as time changes. Okay? So here's my motion map. I'm going to draw a dot showing where the car is at like 0 seconds. So this dot represents where the car was at 0 seconds. And then the next dot is 1 second, 2 seconds, 3 seconds, 4 seconds. And I like, maybe I'll draw one more dot, 5 seconds. Now, do you know why I drew the dots equally spaced? It was pretty simple. As time moved on, did the velocity change? Now, we're just going to assume that the velocity was constant. So my velocity arrows shouldn't change direction, shouldn't change length. I'm just going to do my best to show that here. These are my velocity vectors throughout time, okay? And this is a nice conceptual tool to understand the motion of an object. So this is velocity at 0 seconds. This is the velocity at 1 second, velocity at 2 seconds, velocity at 3 seconds, velocity at 4 seconds, and so on. Okay? And that's a motion map. And again, I like to draw the dots first, and then if it's like constant velocity motion, actually it doesn't matter, whatever kind of motion. If I draw the dots correctly, they should be equally spaced for constant velocity motion. And then I can just draw my arrows, my vectors, halfway to the next dot, and it ends up looking beautiful. Okay? And I'm just going to make a little star here. Notice velocity vectors do not change length or direction in this case. So velocity vectors do not change length or direction in this case. And that's because since the motion is constant velocity. So again, the word velocity implies two things. It implies there's a direction to the motion, and it implies there's a magnitude to motion. Whoops, I just did. There we go. There we go. Okay. Then in the lab, when you collected, you had graphs and equations. So maybe I'll put some graphs on the left side of this slide. I'll put some equations that correspond on the right side. Okay? So the classic graph to describe motion is a position time graph. So I'm going to use x for position just to save space, t for time. In parentheses, I'm going to put the units we used. And then directly below that, I'm going to sketch a velocity versus time graph. Okay? Velocity would be measured in centimeters per second to be consistent. Time would be measured in seconds. Okay? So the position graph, I'm just going to assume my car started at 0 centimeters at 0 seconds and went in the positive direction. So the graph would look something like that, right? And then the corresponding velocity time graph would look how? If you have a constant velocity, your velocity doesn't change, and you'll notice the slope of this graph is constant, right? And the slope of that graph is your constant velocity by definition. And your velocity is constant, so this would be a horizontal line. Okay? And then the value, the number, the value of velocity that you would read from vertical axis is your same constant velocity. So there's a connection between these two graphs. There's a fundamental connection. If you study calculus, you'll know that the slope of a graph is called a derivative. So in calculus, they say, oh, the derivative of a position time graph is your velocity graph. So the equation that would correspond to this graph is the equation of this line. So in the form of y equals mx plus b, that's from algebra class. We rewrite that in physics. This will confuse you. But if you recall that our translation in physics, y is position. And x is your other variable, which is time. So that can get really confusing because the symbols are like backwards from algebra. We never used y equals mx plus b. We would say dependent variable for y, independent variable for x, as read from the graph. So position equals, and then m, as you recall, is like a slope, right? So I would block this in. So we got position equals slope times the other variable time plus, and then the b term is this position here, wherever this line hits the vertical axis. I like to call this the vertical intercept. Fix that. So it's where your line hits the vertical axis. Okay? And just for format, like so we can talk to each other and it makes sense, I'd like us all to use this format for our equations. Okay? We have a dependent variable from our vertical axis, an independent variable from our horizontal axis, and I'd like you to keep those general. Don't put numbers in there. Those are general variables. This shows a relationship between these two variables, position and time, which was actually our purpose for this lab. And instead of slope, I'd like you to put a number that you get from the lab. You could round your slope if you want, round it to something reasonable, the next whole number. So put a number with units inside that bracket where it says slope. Important is to put the units because the units will help you figure out what this slope means. And then for your vertical intercept, I'd also like you to do that. So the things in brackets should be a number with units, okay? Both of those. So both of these things need to be a number with units. And I want you to keep those in brackets to keep them separate from your beautiful equation that shows how position and time are related to one another, okay? And so you'll get a specific equation that might say something like position equals, I don't know, I'm just making this up, 20 centimeters per 1 second, right? In brackets times time plus, I'm just making this up, 5 centimeters. And then a major, I want this in brackets too. A major goal for the class is to use words to describe what this slope and intercept mean. So you would write a sentence like, for every second, and then you would complete that sentence. And then you would want to describe what this means here. And this is I'm going to give you a hint. Notice it's measured in centimeters, this 5 centimeters intercept. Well, that's got to be a position. So this is the position. Well, we were dealing with cars, so position of car, and you should be able to identify a specific moment in time where your results are predicting that was the position of the car. And this equation, we could put any time here. We could plug in any time in seconds, and then the seconds will cancel out, and you'll get a position of the car at any time. On the other hand, you could plug in any position and find out what time the car would be there, okay? So again, leave position and time as variables so that you can use this equation to solve problems, okay? And then for this lower graph of velocity, the equation is actually much simpler. It's just going to be velocity equals some number with units. In this case, it would be, actually I don't need a bracket there. Let me take that bracket out. So it might be like 20 centimeters per second. And that's it. This is the equation for this graph here. Maybe I'll put a 20 there. Okay? And the slope on the position time graph is our 20 centimeters per second as well in this case. So those are a few of the tools we use in physics. I just wanted to give you a brief overview. And give you an idea of what we're looking for. I hope that helps, and thanks for watching. Have a good day.